Look at me in my eyes. Do I look happy? No. No. Do you know why? Because I just did Lab 4. I just did Lab 4. All of it. Yes. And I'm a disembodied head on your screen. I want you guys to listen to something. Ken Carson is a lyrical genius. Let's get into Lab. So first, you should have looked in the Slack and seen a video I posted about using modal sim. Great. Go watch that video. You've watched that video. You followed along, even though I was very tired in the video, and you got modal sim working. I'm proud of you. You can't now you have the right to start Lab 4. That's right. That's right. Lab 4 isn't hard, it's just a lot of VHDL. If you have just been copy pasting what I've been telling you to do all semester, Lab 4 is very hard, but hopefully you haven't been doing that. I'm gonna plug my computer in. We're gonna get started. First, I'm gonna show you guys what Lab 4 looks like working. That's right. You guys are working towards this. What is this? This is the most confusing thing ever when you're holding it in your hand because does this work? Dude, I don't know. I had to test it. So we have two registers. God, no. Two registers, A and B. We have the output of the ALU and we have the input bus. The input bus is probably the most easy to understand. What is this? This is the wrong side. When we flip this, this is 4, 2, and 1. So we can, input 3-bit numbers. 101 is 5, right? 011 is 3. Nice and easy. 111 is 7. Okay, that's the input bus. We can put numbers into the CPU. We can take the input bus. Let's say we want to load. Make sure I'm doing this right. It's the bottom, top button. Okay. Let's say so. It's the top button. Okay, yeah. So let's say we want to take the number 4 from the input bus and stick it into registers A and B. We just click the clock, and you'll notice that 4 got loaded into both of them. What if we only want to load 4 into one of them? Well, there's a way to hold A and B. I'm going to hit this handy reset. Nice. And this middle thing is the output. And right now I have it set to be the negation of reg A, which means 0000 negated is actually 1111, which is hex F, which is why we're seeing an F here. I can also AND them to the output, and that would, 0 and 0 is 0. That's what's happening there. I'm going to show you guys me loading two numbers into. I'm going to load a number into reg A, and I'm going to probably shift it left. It's pretty cool. So let's load a 6. So I've set 6 up on the input bus, and I've set where reg B will hold. It'll stay the same, and reg A will load. We're going to load 6, and you'll see I loaded 6. Okay. And then I'm going to hold reg A, which looks like flipping this switch. Now, no matter how much I press, nothing happens. If I change the input bus over here, which is like 0, nothing happens. That 6 is staying there. All right, now I think left shift is like, yeah, it's this configuration. Left shifting is the same as multiplying by 2. 6 times 2 is 12, which is C in hex. Okay, there's that. Notice that happened without a clock signal. Finally, we're going to load C into reg B, which looks like 2, 3, 4, 5. We're going to do this. I'm going to flip some switches that I know what they mean, and we're going to load 6 into reg, or C into reg B. Nothing happened. All right, I'm going to shoot myself. That's because I think this is the right way. Yep, load C into reg B. I just had it wrong. So it was an issue with my implementation. Issue with me. Guys, this semester's killing me. It's really taking a toll on me. Anyways, C is 1100. 6 is 0110. Okay. Are you not good at visualizing binary numbers in your head? That's okay. Because I'm gonna share my screen. Okay. 1100. Guys, I have an exam tomorrow and I haven't studied yet. So these numbers, when you add them, you'd expect us to get, binary for 4. And so I'm gonna add them and 3. No, it's not. This is anding them. Yeah, there we go. I'm going to and them, and you can see it's four. We're building a little mini computer. DE10 gets pretty hot. I'm not gonna lie. So hot that I'm gonna unplug it, and we're gonna get to the lab. Hopefully that demo explained what we're doing. Basically, we can flip switches and then press a button. The switches are a command, and the button runs the command. So if I have the command hold reg B and load input bus into reg A, and I press the button, it does that. And if I say take reg B, reg A, add them, and then put the output into reg B, it's that. Super, super duper cool. Okay. Close this. That's what we're working towards. Close Zoom. I don't think I need that. I'll leave it for now. Quartus. Close the programmer. We won't be seeing it for a long time. Same thing. Here's some code for later. There's someone in here. I always hear people in my private Zoom meeting. It scares me. Start reading. 50 points. Overview. Basically a yap fest. We're building an arithmetic logic unit. It can perform logical ands, ors, nots, addition, subtraction, twos complement, bit shifting. It's the brain. Computers get one of them. Computers get one of them. Registers. This is a D flip flop. It's four D flip flops, but a little bit fancier. We'll see. Putting it together. I mean, why are you watching this video? For me to show you to put it together. So design the ALU and VHDL. Okay. I'm going to do this. First, you're going to see this diagram they tell you to finish. How do I finish it, Joe? I'll tell you how. Look at these operations. 1, 2, 3, 4, 5, 6, 7, 8. Not and or add. Out A, literally just put A out. Out B, same. Shift left, shift right. Logical, ignore it. Just move everything. If you need to shift out a number, shift it out and shift a zero in. That's it. Look at this. This is very nearly complete. What's the issue? One, two, I see four inner rectangles. Right? This was very beautifully drawn, by the way. Whoever drew this must have had a lot better than paint on their computer. Okay. So basically, this whole thing is done. It's just that there's only four commands here. You guys see that? But there should be eight. Okay. How else are you going to finish it? Well, not only uses A and uses A and B, or uses A and B, add uses A and B. Basically, take this, draw it again, but now I want to see eight boxes. 1, 2, 3, 4, 5, 6, 7, 8. And some of these only use A. This guy only uses A. Some of them only use B. Some of them only use A. So do not put A and B into an operation that only uses A. That's stupid. Everything else is complete. You're just adding four boxes and pointing A and accordingly. Probably use blue. I like the orange and blue now that I'm looking at it. So this will get you a resounding not many points, but go ahead and do it. The main portion of the lab, the thing that's worth points, is VHDL design of the ALU with a simulation according to the following operations. Okay. So essentially, it gives us this. This is what you're given, right? This picture. Okay. These operations. And I'm going to actually grab them and stick them in paint. You need to be able to take this picture, kind of cobble together, and I like get some ideas organized. This table. And from this, you should be able to take this and make the VHDL for an ALU. We have some simulating stuff down here. Okay. Capiche? Capiche. So I'm going to open up Quartus. I've got Paint open. We've got Zoom open. Notepad's open. Chrome is open. Let's chill. Let's chill. Okay. So how am I going to do this? What's the best way to do this? I'm going to go to BUP. I'm going to take Lab4 PhD, and I'm going to copy the entire thing into a notepad, which I'm going to save as lab4_2. Additionally, we have lab4_1 here. This is really easy, which is nice. And we're going to get started. So as always, my least favorite thing to do, I spent an hour writing this code. I'm going to delete all of it. and I'm gonna delete the compilation report, get all of this scary stuff out of our face. It's an empty it's an empty project that you set up. No need to think about anything if you use modal sim, just set up Quartus like you did before. We're gonna have two files, and one of them is gonna have some code in it, and we'll see how I handle that later. ALU test bench for Lab4. Here's the test bench. I'll go over this once we're done. So let's get into it. First, same as always, we need our imports. I believe I have them here, but I didn't. So this is why we take our stuff and put it in a notepad because we need our imports. And I don't even need to look. I don't need you wouldn't even need to look or think. You could just say lab4 port and go like this. Okay. And I'm sharing my screen, I'm recording. Okay. That would be kind of scary if I wasn't doing that, guys. Imagine. I'm not making a second video. I'm not engaged like that. So we can see this, but you wouldn't have to look at it because all you have to do is you have to, oops, look at this. Can you tell me the inputs and the outputs when you look at this? Can you? You should. I see one, two, three, four inputs and two outputs. The ALU has no clock. It's just COM logic, combinatorial logic, literally. So we got A, B, C in, and op. So we got A is an in, standard logic, vector. I think it said it was 4 bits. B is exactly the same, right? The CN is just logic, but for reasons we'll see, I want it to be a standard logic vector, 0 down to 0. Now, probably Joe, you're gonna make me angry, Joe. Sorry. What is a 0 down to 0 standard logic vector? Think about it. Put it in your noggin. It's an array. It's an array. Ooh, been standing like all day, bro. It's an array. An array with one element. It can be this or it can be this. It's basically the same as just a 0 or a 1. But we need it for future endeavors. You'll see why. You'll see why. So I'm going to say for all intents and purposes, um, it's a standard logic, right? It's one thing. Anyways, we've got the C out. No need to do that fancy garbage with this with the C out, right? It's just a standard logic. And then we have, I'll call it F. Yeah, I'll call it ALU out. So output standard logic vector 3 down to 0. And don't forget, no semicolon here. Nope, none. Yeah. Okay. Does this confuse you? And we got, of course, end Lab4. Does this confuse you? Because it should not. This is basic. You should be able to read this thing, and you should be able to be like, okay, duh, right? I understand this. Okay. Moving on to some less basic stuff, we have the architecture. Architecture behavioral of Lab4 is begin and the behavioral. So I said that we were gonna that it was completely combinatorial, and it's true. But we're gonna use a process block anyways. Process. If you don't understand why that's kind of a contradiction, then you're good. But if you think like, wait a minute, you told me the processes were for sequential and synchronous stuff, and you're telling me it's purely combinatorial, there's a trick we're going to use. It ends up being purely combinatorial. It's going to make our life easier. But for all intents and purposes, the ALU is ands, ors, and nots. There's no flip-flops in there. The ALU is just pure combinatorial logic, muxes, stuff like that. Stuff that has instant feedback in the clock. You do something to the ALU, it does something back. And so how do we kind of encode that in the process block? We make every single input part of the sensitivity list, right? A, B, C, N. When A changes, the output changes. When B changes, the output changes. When C N changes, the output changes. Gee, this looks a lot like a combinatorial circuit, right? Anyways, so we're gonna have a little case statement. We're gonna do that on the Fun fact, your friendly Hi Joe's an idiot. We need our opcode. All right, that's an in standard logic vector 2 down to 0. I'm like, Joe, where'd you pull that out of? And I pulled it out of here. Right? I just missed it. 1, 2, 3, 4 arrows pointing in means we should have 1, 2, 3, 4 ins. My bad. Anyways, the opcode, case opcode, I think you say like is and then do like a when. I'm not a VHDL expert. When, thing, then we do something in here. And then we can do something. Excuse me. Just ate. Just kidding. I just worked for Lab4 for hours. Okay. It's been a rough weekend. All right. Please leave a like on this video. Please. I'm joking. So case, what's the case? Well, it's a standard logic vector, so it's like when it's 0, 0, 0, we should do something. When it's 0, 0, 1, we should do something. Or add right? Cool. So it's the best way to like copy. I wish I might start sending you guys videos in Vim. We'll see. Okay, so we're gonna do something on 0, 1, 2, 3, 4, counting in binary if you can't tell, 5. This is pretty cool, right? And so it kind of becomes clear what's the code sort of conveys its meaning on its own. Is I guess what I'm trying to get at, right? Um, you can basically see that if you've gotten this far, well, in the 0, 0, we're gonna have to make f equal not a. Or in 0, 0, 1, we're gonna have to make f equal a and b all the way down, right? This isn't bad. This is not challenging. Maybe understanding you need a process block when we're telling you it's purely calm is bad, but I'd expect that most of you should be able to do this, this. There are some hard ones. The adding plus the C in with the C out, that's a little bit challenging. These are non-trivial, right? But these, maybe try and do on your own. See if you can get them because they're not that bad. We'll do the easy ones first, of course, with some test compiling. So 0, 0, 0 just means output not A. And so, I mean, are you surprised by what I wrote? You shouldn't be. It's nice and easy. And this one might be a little confusing, but you can actually just do A and B for standard logic vectors. Really not that bad. And it's a similar story for OR, right? This is not really that bad. This is, so far, pretty easy. Setting up modal sim was probably harder than this, in my humble opinion. Okay, adding, meh. We're gonna leave the adding thing alone. Output A, output B. Okay, that's nice. F becomes A, and F becomes B. Pretty cool. Logical shift left, logical shift right. Right? I don't think we want to do that yet. So let's tackle one thing at a time. Adding, right? F is going to be A plus B. We can't do that. We can't do that because A and B are standard logic vectors, and standard logic vectors don't support numerical operations. So what are we going to do? We're just going to unsigned A, unsigned B. You might be wondering, what is this thing we're doing? This is a function called unsigned. Maybe it's more like a cast, but I think you should think of it as a function. Unsigned takes in several different types. One of the types it takes in is a standard logic vector, right? And remember, we're doing plus the carry n, so unsigned, right? One of the types it does not accept is standard logic, okay? If we had Cn as just standard logic like this, right? We could not cast a single bit to unsigned. Now, that's stupid. We can cast a single bit to unsigned. All we have to do is grab this. Oh, what did I do? All we have to do is grab this standard logic and make it a standard logic vector. And all of a sudden, this single bit can be represented as an unsigned 0, 1. So a little bit frustrating, but it's the quirks of VHDL. And so we're using a 1-bit list instead of just a 1 bit. It's okay. And we want to cast this back to standard logic vector because our answer is a standard logic vector. Pretty cool. Right? Okay. Now, what about the C out? For now, I mean, C out is just going to be 0. I'm not bothering with it right now. We can bother with it in a minute. That's okay. Remember, it said C out should be 0 all the time. So these cases I've been skipping by, stick a C out 0 in them. Don't forget your semicolons. All right, and that applies to the A output, that applies to the B output, and now we need to look at left shifts and right shift. I got no idea how to do a left shift or right shift in VHL. I looked that shit up on Chat GPT. I do not care. So SRL, SOL. Cool. Okay. So there's basically SOL, SRL. So what do these stand for? Shift, left, logical. Okay. Shift, right, logical. That logical is important because there's such thing as a arithmetic shift, which is different than a logical shift, but it's fine for now. So what do? We standard logic. Let's not do that yet. We just unsigned A. We shift it left once, right? And unsigned B. We shift it. Shift right logical. We shift it right once. Okay. The bit again is that standard logic vectors are very simple, very fast, very dumb. They don't support logical shifting. They just support, being stupid and moving around and stuff. If we want to do a shift, we have to cast it to unsigned. The same way we have to go back to standard logic world after doing that, or standard logic vector world, we just standard logic vector. If you want to know how I learned this, I asked ChatGPT. It told me. Standard, I'm not a VHDL god. Vector. So hopefully these operations make sense and make sure that we grab our C out. If not how, then what, right? Logical shifting, you guys should understand pretty intuitively, right? If you don't, I'll do a quick example for you. You can totally feel free to skip this if you already understand, but maybe you've never even heard of the term shift. We've got the number 0, 1, 1, 0, and we shift it right. It just becomes 0, 0, 1, 1, right? This bit goes here, this bit disappears, this bit goes here, a 0 comes in, right? We're kind of, okay. And when we're shifting right, 0, 1, 1, or when we're shifting left, 0, 1, 1, I mean, this bit goes here, this bit goes here, we get 1, 1, 0, 0, right? Everything moved over and a 0 came in, right? Whenever something shifted out, it dies, it leaves forever. Whenever something shifted in a logical shift, it's a 0. We won't get into arithmetic shifting today. Hopefully that makes sense. And it's literally just baked into VHDL because it's such a common operation. Fun fact, shifting left is multiplying by 2, and shifting right is dividing by 2. But hopefully you guys didn't think that was hard because we're done. Let's compile. While we compile, I'm going to ask you guys to please fill out your Gator evals. Listen, I get paid not enough. I've been paid once so far, the whole semester. Object F is used, but it's not declared. And it's like, So we're gonna do something a little bit risky, but it's fine. A little fine replace. I'm gonna replace F with ALU out. And hopefully I didn't replace, like if I wrote the word off, it would be O, ALU out, ALU out. But we'll see. It's okay. It's okay. Everything's fine. Filing again. Oh, one error. Synthesis was yeah, look. This was OF, and I replaced it with OALU out. Kind of funny. I'm happy that I had to replace one thing instead of 7, 8. It's okay. Typos happen. They're a part of writing VHDL, especially in Quartus. I don't know why you guys write VHDL in Quartus. I would never do that. But look, compiled no errors. Okay. So assuming we didn't make any mistakes and you're like kind of confident in what you did, and we remember that this is wrong. Keep in mind this is wrong, right? Because if we perform an addition and there's a carry, we need to set the KC out accordingly. But I digress. Let's move on to the test bench and then we'll come back to that. Okay, so reading the document, it says that the only stuff you guys are responsible for one is this thing, but everything you're like really responsible for is this pre-lab. Follow the Quest to Sim tutorial. You watched my old video and you're using Modal Sim because you're awesome. You watched the other video. Create the VHDL. If you just followed along at this point, I can give you 10 points. Whee! Provide annotated simulations for the operation described in part one. So a test bench for operation is provided to you and you must modify it. So do we want to use the test bench that was provided? I don't know. I haven't looked at it. Let's go to Lab4. Cool. G Automa. Custom docs. So that's not what we want. They don't run anything sensitive while I'm in here. So there's a test bench here. TB stands for test bench. So I'll download that and we can open that in VHDL and see what that looks like. Hey, Windows Defender, can you please shut up? Oh my God. The whole internet is convinced that VHDL files are like these really big, scary things. And it's literally the file is corrupted. Shut up! Watch, the file is corrupted. Edit in Notepad. This is corrupted, really? Shut up. So I'm like looking and I guess like oh yeah, like I'm not using this. Sorry guys. Respectfully, it's just not I don't have it in me to deal with the code written by people, other people. So what's the test bench file look like? Here's the one I wrote. It's probably better. I'm gonna copy it and I'm gonna stick it into. Oh no, I closed Notepad. Did I lose the working code? Could be scary. No, it's here. It's chill. Okay. I'm putting this here. It's like chill. I'm gonna delete almost everything. There we go. Okay. So test bench, literally just file new VHDL file. Call it the naming convention, which is not required, but I will be very angry if I see anything else. Do not do anything else. You make me miserable. The name of the file you're testing and TB underscore. So TB underscore the name of the file you're testing. So first we're going to start with our imports. Nice and easy. We're going to have an entity called this. Fun fact, the entity is empty. So that's nice. Let me make sure I'm doing this right. It just says is end. Even better. Let's make it a one-liner. Entity lab is end. So an empty entity. And now we have an architecture. This is like a function with no inputs, right? It's like a, anyways, or outputs. Kind of weird. Architecture, behavioral test bench is begin and behavioral. Oh. And so how do test benches work? You make a component of the thing you want to test, you make test signals, and that's it. I promise that's it. So the first thing we're going to do is I think like a little component uh Lab4 port, something like that. I don't memorize VHDL. Sorry guys. End component Lab4. Component Lab4 is port. Whatever you say. Boom. And what do we stick in here? Well, we go to the Lab4 thing. We grab all of this, excluding the trailing parenthesis and semicolon, and we just stick it in here, right? We're just telling it about the inputs and the outputs. Not hard at all. Make sure you hit a little end component. Make sure you've got this kind of ending, right? I had it like this. I pasted this stuff in. I didn't duplicate my parentheses, no issues like that. Okay. Next, we're going to define some signals. You might be like, Joe, what signals are we going to define? Well, we need input and output, right? So boom. Here are the signals. Like, Joe, that's what you just pasted. Yep. Yep, you're correct. it is. Make sure to put a semicolon here, and we're literally just going to say sig null on all of these. Boom, 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 boom. Now, the fact that they're named the same can be confusing, but right now they're doing nothing, so it's okay. We're going to go into the test bench. We're going to have our lab4 inst port map. It's a thing of lab4 or port map. That's an amp port map. This. And what does lab4 have? Well, it has A, B, it's got CN, it's got opcode, it's got cout, it's got ALU out. Okay, so those are the signals. Like this on the left-hand side of the arrow represents this. And we want to say, well, what should we put in the input? And this cout on the left-hand side of the arrow represents the output. Where should the output go, right? And the answer is these conveniently named signals where the signal is named exactly what the input's named. Typically, you don't do this you don't want to confuse yourself or other people reading your code unless, you're the dude who wrote the code for like Lab 3, who I hate. If you guys watch the video, you know about the drama between me and him. The worst coder alive. I hate that dude, but it's okay. Boom, port map. Okay, now what do we do? That's a great question. I think we're like low key done. Yep, yep, yep. Okay, so I'm gonna do one of these and then I'm gonna copy paste it because I'm tired and I don't want to do it. So we have like a little process, begin, end process. And how do test benches work? Well, first you do this rigmarole where you have the empty entity, an architecture which defines the thing you want to test as a component. You define signals which you can control so that you control all the inputs and measure all the outputs of the thing you want to test. And then you have a process. That's it, okay? Entity, component, signals, and your test. Testing happens here, right? Everything else, maybe keep this, a copy of this, and whenever you want to make a new test bench, just change the component to match the thing you want to test, change the signals to match the inputs and outputs of the component, and change your port map and the names here, of course. And then we're going to get to the testing. So what are we doing with the testing? How did the testing work? Literally, you just like do something like this. I'm going to write it and I'm going to explain it. A is 0, and B is going to get a similar treatment. B is going to get a similar treatment. Oops. I'm going to make CN 0, and I'm going to make opcode 0. And then I'm going to wait some amount of time. The lab doc says to wait for 10 nanoseconds. Sure. Sure, I don't mind that. Sure. All right. This is a test. We're saying, okay, look here. Look here. We're going to make A 0. We're going to make B 0. We're going to make the C in 0. We're going to make the opcode 0. Okay. And so the opcode being 0 means we're going to do not A because A is 0, like this. We negate each of these to get 1, 1, 1, 1. We expect the output to be 1, 1, 1, 1. Okay. And the lab document, if you read it with your eyes, hold on, has some tests it wants you to do. It says use these tests in QuestaSim, right? And you'll notice I just did the first one for you. A equals 0, B equals 0, opcode equals 0, and a little bit of a hint, Cn equals 0 if it's not mentioned. So the only time Cn will not be 0 is right here. Cool. You guys know how to copy paste things, so I'm just gonna. You don't see nothing. Boom, right? But there's literally nothing new, right? I just oops. It's just A, B, opcode CN, then wait for 10 nanoseconds, okay? Then A, B, opcode CN, wait for 10 nanoseconds. A, B, opcode CN, wait for 10 nanoseconds. Okay. There's nothing different about this block than the first block, just that they specify different values for A, B, the opcode, and CN. Okay. So now we're gonna do a little silly goofy compile. Yes, make sure your test bench compiles here first. And we'll get to finishing part 1 of the lab. Pretty exciting. quite exciting. Yes, I know. Oh no, there's an error. Signal A, near text in, expecting an identifier. In is reserved word. Let me think. Yeah, of course it's a reserved word, you stupid thing. In, I'm not importing, I am. This is the only error. Syntax error near text in, expecting an identifier. In is reserved keyword. That's just joyous. How did I? Does your ending component not have a semicolon? No, it does. This guy's ended correctly. Mm-hmm. Okay. Is port. I can't believe components get is port. Maybe I'm tripping. Component Lab4 is port. Hmm. This is great. I don't know what's wrong. Signal A. Probably because nope. Says text in. Oh, duh. Signals aren't inputs or outputs. Oops. So having ins on them doesn't really make sense. Having outs on them doesn't really make sense. A signal is just a wire. It is dangerous to hook two outputs to a signal or something like that, but signals are just wires with types. Whether we hook them to inputs or outputs is irrelevant, obviously. Like according to this line, right? We're setting A to the signal A. A is an input. We're setting ALU out to the signal ALU out, which is an output. So good little bit of debugging there. Ugh, my back hurts. Ugh, that's okay. It's a crispy 8 p.m. Submission comment. You're getting ignored. Action items. Ignored. I gotta. Is someone in here? That would be terrifying. No. Participants one. It's just me. Someone messaged me like they're in here. I'm just gonna hit him with like a little afraid emoji. He doesn't know I'm recording a very serious lecture. He doesn't know. Oh no, op is used but not declared. Oh no. Why is that? I called it opcode. All right, that's fine. So just scroll down, little op with opcode. Place all. Boom. I don't know what that was all about. Frankly, frankly terrifying. Yeah. He said, I see you. I'm alone in my dorm room. I'm not alone. But oh no, opcode is used but not declared. Oh no. Opcode code. That's funny. Opcode code. Opcode code. The wonders of Quartus right here, guys. Uh, yeah. Um, engineering was not worth it. Opcode, opcode. Formal opcode does not exist. I don't believe you. Signal opcode code. That would be why. If you guys want to make like a triage of people who transfer to business, it's a great proposal. Please email me at my student email about switching to business. It looks like it compiled. That was a lot harder than it should have been. Probably because I copy pasted some old code where I used different variable names. Let's open ModalSim. We've written our test bench. We simulated with ModalSim. Annotate the simulation. We're good. So you open ModalSim, you're greeted some hideous thing like this. Actually, you're greeted because I've been doing this. I'm good at this, but I'm gonna do a little file, a little new project. We're gonna go there. I'm gonna call it on the video. I'm goaded. I'm gonna call it Ken Carson. He said that, bro. It's a fire song. I'm gonna make a folder for it called Ken Carson, Ken Cranston, Cranston, Ken Cranston. Yeah, Ken Cranston. You go inside of it. It's called Ken Cranston. That's all you do. Don't change. Make sure this is here. Click OK. And add existing file. We're gonna browse. We're gonna go to. I don't know what we're gonna go to. What did I call it? Lab 4? Probably. We have our test bench and we have probably just Lab 4. Like this. I bet these are the right files. And you just click open. I was using control click to get them both at the same time. Reference from current location is what you want. Do not copy to current directory. Click OK. You're going to close this. You're going to get two files here. There's a question mark on them. We have to compile them. Compile all. And oh no, it shits itself. Look at this. The test bench compiled, but Lab 4 didn't. Right? This happened to me and I was very confused. So I was like, let me go back over here, go to Lab 4. Let me go to project, set as top level entity. This is the thought process and compile. And I was like, the fact that it's compiling in Quartus, but not in ModalSim, what's going on? And so I compiled. And I'm going to spoil it for you. This top level anything was not the issue. No, there's a different issue, and that's Quartus and ModalSim are using different compilers. Okay, you'll see compiled with zero errors. And so like, oh, it must have been a fluke. Let me compile all. It was not a fluke. So how do we know what the error was if we're dealing with two different compilers? And is it possible for us to make them both happy at the same time? The answer is typically yes. And so you just go to compile and compile report or compile summary. I like summary. You make this full screen. It says something, it's like error suppressible. And it says something like there's an issue in lab4.bhdl at line 19. It says case statement choices cover 8 of 729 cases. So we go to VHDL, we go to like line 19. It says this case. It says it's not extensive. And so let's check. Did I maybe forget a case? Did I duplicate something on accident? We have 0, 1, 2, 3, 4, 5, 6, 7. I mean, what the hell else could there be, right? There could be other stuff. See, standard logic isn't just a bit. It's not just 0 or 1. It can be high resistance. It can be weak low, high low, or strong low. It can be weak high, strong high. It can be unknown, right? And so we have to say here others is going to get, and what should everything else behave like, right? I'll just say it should act like the zero case. I don't really care. This isn't going to happen on our DE10, but it's important to realize, right? This is important. Let's compile this while I talk about why it's important. Um, when we're working with real circuits that aren't just one magic DE10 light, there's noise, things get pulled low, things get pulled high, there's crosstalk, things unplug, and they're left high Z, they're left floating. Okay, everything's not a 0 or 1, as much as we'd like to be. Okay, there's an error, says near others. So I did something wrong. Let's see how I did it in here. My case statement for Lab 4. I said, oh, it's when others. And that's basically just the big else statement, right, at your case. But in the real world, stuff isn't zeros and ones. There's a Chinese proverb. Yes, I got it out of a Chinese fortune cookie. It says digital components are made up of analog parts, and it's really deep if you think about it while you're but you know, you know. So now it compiles here, and we're like, okay, I'm feeling brave. Let me try. Oh my God, I'm in window hell. Where was I? This one. Okay, we'll try compiling it again. Compile all, and we'll see that we got rid of that error. So when you're working with ModalSim and it works in Quartus, it doesn't work in ModalSim, read the compile log and fix it. It's not that bad. So what do we do now? Everything's compiled. We see check marks and everything. We're going to simulate, start simulation. We're gonna go to work. and then just click on the test bench. Do not click on behavior. Click on the test bench. Click OK. Um, this great window will open up. You can tell by the way this window loads that it's not using a graphics card, which tells me that this software was made by a fool. Um, I clicked on this little pop out button. You can see them all over, like right here where my mouse is. And I clicked on that for this guy. I clicked pop out, and I'll dock him, and you'll see he pops in. This is the default. This is what you would see, right? So I clicked right here and I popped him out, and then I can full screen him, and this is where our simulation will be. But Joe, it's not there. Yeah, I know. I know. I'm getting there. So you basically have to go to like sim something. Yeah, sim default. You have to find this buried in here. Right click on TB Lab4, click add wave. Go back to here. You should see the signals popped up. Now they're named a little bit weird, but we see our ALU out, our C out. We see our opcode, our C, and our A or B. So what do we do now? We move the dock. Can I move the zoom dock? I can. Get this shit out of my face. Um, yeah, that's chill. And we put it on 100 nanoseconds, not 100 picoseconds, because we were working with nanoseconds in our thing. We click enter and we check, and I guess hitting enter isn't enough to update it. So we click this paper with a down. It says run. I clicked it. You go here, and we see this. Now you're gonna be like, Joe. And we're like, what? What could the problem be now? Possibly. You'd be like, Joe, it's not working. Why would it not be working? Remember, we put 5 different test values in. And look at these. They didn't change at all. Control, scroll wheel, keep scroll wheeling, and you'll notice that it totally did run. We just have to kind of walk back a little, all the way to 0. And here we are, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It ran twice. So it's okay. And you'll see that it's for the first three, like for example, C in for these first three, don't do anything there, is 0. Right, and I'm gonna grab this and we can move to paint where I like to live. But this is what we have, right? And we'll go to paint and we're basically done with part 1. So I'm gonna get rid of our little mind palace and paint here. Anyone else here watch Sherlock Holmes? Okay. And so let's compare the first and the fourth. Okay, let's look at the first and the fourth. Not really comparing them. We're just kind of like, do they look like they should? So here's the first. We see that A, B, and C enter 0, and the opcode is 0. Now, I just remember that's how it was. I didn't make a mistake there. And when the opcode is 0, we just put the negation of A onto the output bus. That's here. All zeros negated is all ones. Nice and easy. Okay, let's look at the fourth one. Okay, we've got the binary for 5 in A, and we've got the binary for 4 in B, and we've got a C in of 1. Okay, and my best friend is messaging me. So my best friend's messaging me. It's chill. Um, Maybe not my best friend, but we're gonna add these, and you'd expect that we get 10, right? A. Maybe you'd expect we get A, right? 10 is A, and this is A. Perfect. And with 0011, remember, it means add. Sorry, my best friend's texting me again. He said, "How you been?" I'll message him. This is like your ex texting you, but like it's not something I hate. Oh, my dog. I'll tell my dog dressed up for Halloween. Anyways, kind of low key makes me sad, but it's chill. So are things working? Or is it? Let's do one last thing. And that is if you turn this in, I'd probably give you full points. But if you're not in my lab and you're watching this, sucks to be you. Remember our C out equaling 0. We actually want the C out to not equal 0 all the time. If there was a carry, we want our C out to be true. So if thing, then C out, L, and if. Right? if overflow, if carry bit, basically, then C out equal 1, else we'll just say that C out is going to get a 0, right? And otherwise, C out is going to get a 1. So how do we check this? Well, we already have the sum here. And so let's just check if the sum is greater than or equal to 15. If the sum is bigger than 15, right? I'm going to compile this while I explain it. Basically, here's the biggest number. Here's the biggest number we can represent in binary and with 4 bits. That's 15, right? So if the answer is 16, we must need 5 bits to represent it. There must be a carry bit. That's the 5th bit, right? Something like that. Okay. Nice and simple. Really shouldn't have left it. It's not that bad to explain. It is kind of weird because I don't know if you guys were taught to work with numbers, but it's just, is the sum bigger than 15? Nice programming language. It worked. Beautiful. I'm going to close modal sim. My friend's still texting me. He says I got ops. SolidWorks certification. Let's go. Let's go. Let's go, bro. I'm proud of you for that. This is my boy, so it's like we proud of him. But modal, that's model. Modal. Modal sim. You can search models up on your computer. Model. Apparently not. Anyways, boom, it opens the project up. It knows we changed the file, so we compile it. No issues. Simulate. Start sim. Work. I'm kind of ignoring my friend right now. I feel kind of bad. Default. Okay. It opens. We wait for it to load. It loads 100 nanoseconds is what we want. We click run. That window didn't open because we didn't click here and then click add wave, which opened it and inserted the things. And then we click run and then we look here and we zoom out a crap ton and we swipe all the way over. And here are our things. Now they're kind of floating in space because I clicked one once, and this is the 100 nanoseconds of simulation that ran with no signals. So here's the next 100 seconds, right? If you want to refresh it, make it like a clean slate, go ahead and restart the program. I don't know how to refresh it. There's probably a button here that does that. I couldn't care less. Break, simulate. It does this all the time. You don't even press the button. Anyways, here's our sim, and you realize it looks the same, and our sum is still 10 because there wasn't a carry, and the carry out's 0 the whole time. Pretty chill. You're gonna take the simulation, you're gonna simulate, you're gonna annotate it. Boom, annotate. You're gonna like take a screenshot of this or something, ideally like where it's lined up with here so you can grab these. You're gonna take it into paint like this, and you're basically gonna do this, right? You're gonna so like 5 plus 4 plus 1 equal A, and that's this. You're gonna say, hey, this line is 0, 0, 0, 0, like putting a bar in between, not, and that gives F or 1, 1, 1, 1. So for each of the commands, there's command 1, 2, 3, 4, and 5. What's the command? What's it doing? What's the result? Basically, just say A and B, A or B, the 5 commands. How do you know what the commands are? Go to the lab and read this table. How do you know which maps to which? The opcode, right? All the way across. This is A, this is B, this is C, and this is the opcode. This is C out. Let's explain what it's doing. I don't think the first part's that hard, aside from modal sim. And I'm going to pause the recording really quickly so I can message my friend that I'm busy. He made a song called Get Busy. Pause. So you made it this far. Congratulations. You've done part 1. So cool. That means you've watched my previous video, coded along with me, created a simulation and a test bench. Finally, we're going to create the data path according to its design, and I'm not going over the extra credit. I do not care. Submit your pre-lab questions as a PDF and archive your course projects. You can do the appendix. Cool. So the first thing you're going to do after finishing this part of the lab and having your screenshot and putting it all in a Word doc is you're also going to go here. You're going to go to project, You're going to go to Archive Project, and you're going to name it Lab4 Part 1, or whatever you want. And you click Archive, and it's going to say Project 1 successfully archived. Boom. You're going to turn that file in. It's a .quar file. Do not turn it a VHDL file. Do not turn a QPF file. That's stupid. You're going to turn a QAR file. I can't see myself. I'm so sad. Let me do that. You're going to turn a QAR file, part 1. Now we're going to get on to part 2, but my boy, fiending for arm gains. He's 164. Hey. You might be bigger now. Okay. Okay. So, part 2. Part 2 tells us to build silly, goofy thing. It kind of throws you in the deep end. It's not cool. Tootling it. It asks us to build this. Right. Okay, what even is this? Okay, we built this ALU part, right? This looks pretty similar. We built this. It wants us to build a Reg A, a Reg B, a MUX 1, a MUX 2, and do some advanced looking wiring. Essentially, these are two registers that feed the ALU, and so we can kind of like, you know what, you'll see. We can basically, the registers are Reg A and Reg B are going to replace A and B in the ALU. And this way, right, this way, if we want to do like A plus B times 3, we can do A plus B, store that in here, and store 3 in here, and then do A times B, which isn't something we could actually do, maybe plus 3, right? A plus B plus 3, right? We can store A in here, B in here, perform the add, put that back into A, then store 3 into here, and then perform that. It gives us more control, right? We can use the result of the previous calculation for the next calculation. We can also use an input bus to determine our next calculation. So the wiring, I'd argue, is the most difficult part. So let's get into it. So basically, we're gonna make a bunch of new files, which means I'm gonna paste a bunch. I'm gonna text my friend to hold on. I'm planning on having my DD lab section Monday. This dude's a goat. Triceps looking brazy. Looking good, bro. I have that same toothbrush. We are twins. Sorry, guys. Anyways, so what I'm gonna do, I'm gonna like save it as something. I don't know what this is. What is this file? This is the TB, the test bench. Okay. And so I'm opening these up so we can actually like get working. So the test bench was only for part 1. We don't need it anymore. Lab 4, I'm gonna leave for now. And we're gonna start. I'm opening files because they already exist for me. You are gonna make them new files. I'm gonna open up ALU, Big Mux, Reg, the decode. Yeah. Okay. So now they're open. First, 7 segment decode. I called it 7 segment decode, and this was named differently. I'd rename it and rename it everywhere. Where did I get this file? I went to Canvas. I went Files. I went Lab4 Components, and I went 7 seg decode. I'm not using this piece of garbage. Newman wrote it. It's not a piece of garbage. I lied. I'm not using this glorious one. I'm making my own. But this file right here, I just downloaded it, copy pasted it, or whatever. It's chill, right? Um, and that is exactly what you'll find right here. So author Newman Waters, that's how you know it's absolutely glorious with no errors. We're closing this file. We won't look at it again. Make that file, copy paste. My friend's texting me. Bro keeps texting me about things I'm sad about. It's so uncool, bro. So uncool. How do I pause the recording? Hello? Okay, I'm back. Um, so I mean, let's just start going through it. So ALU will be the easiest. I'm going to take the whole file, start from scratch, just so problem feels approachable. Close Notepad like a gene. Oh no, I didn't. Here it is. So here's the ALU. Okay, ALU.vhtl, and I hate to break it to you, but ALU is easy because we just made an ALU. Look, it's all here. Literally, just take all of Lab4. Okay, paste it in here. Okay, literally, and then just do a little find anywhere it says Lab4 in this file. Click replace. Type ALU and then replace all. And then go to zoom and minimize it so you can stare at yourself. And I think that's it, right? Okay, so if you did part one, this file is quite easy. Friend keeps texting me. 175 IDK maybe cut in. Because like he's talking about trying to add 40, 50, 60 pounds to his bench. Probably this dude. I don't want to. Don't. I don't. And don't easy. Lock in. He's talking about benching 225, bro. Needs to lock in. It's not that hard. It's really hard. I've been doing 3 days. That's valid. He doesn't understand. He thinks everything's about him. I'm gonna put his email in the description of this video. You should email him. Just try back by legs. He's doing PPL. So PPL. This loser. All right, so this is kind of nice. Let's do this one next. Big mucks. Big mucks. We're gonna do big mucks next. Mucks. I'm just saving it. You guys don't have to do that. So what's like a mux? I think the first thing we're gonna end up doing is importing things. Feel bad ghosting. I'm just gonna be honest with him, bro. Yeah, tragic. Um, I gotta finish giving this lecture. It's my turn now. My question now. I'll be back. Lock in now. Okay. Chill. Anyways, we're doing the big mucks. ALU is nice and easy because we already built it. We already talked about the inputs, talked about the outputs, and talked about the VHDL implementation. But but now, how to make big mucks? Well, what is big mucks? Let's go look. It's this, right? It's got one, two, three, four inputs, five inputs, and two and one output. Okay. And literally, we just what is a mux, right? It's a digital switch. It's a data switch. And so literally all it does goes like this. And depending on this value here, it just either does this, where it connects this one, or it connects this one, or it connects this one, or it connects this one. Right? That's all it's doing. So now that we understand what it does, how many inputs it has, and all of these inputs are going to end up being 4-bit. How do I know that? I mean, read the schematic and follow them around, right? This guy comes from here, this is 4-bit. This guy comes from here, it's 4-bit. This guy comes from here, it's 4-bit. And this guy comes from here, it's 4-bit. So we have an entity that I'm going to call Big Mux. Support. Like that. And it's going to have the select lines, which is an in standard logic vector of 1 down to 2. Okay, and we're gonna have A, which is an in standard logic vector of 3 down to 0. Oops. There's A. Uh, B, C, D, and then we're gonna have our mux out, which is an output, right? Hopefully, your guys are getting to the point where you can type these in your sleep. Don't forget the semicolon shouldn't be here. My friend, get back to me. I get it right. Oh boy. All right. So now we're gonna make the architecture for this entity, And something like that. And like, how should the mux work? I think I don't even have to look at the thing. I think I just know. We're gonna have that process that depends on the select line. Um, begin, end process, right? And it's literally just gonna be like case cell is, how did we do case statements before? It's just case thing is. Let's get rid of this. So case cell is, and we have like a when that points to a like a that, and then boom, something like this, and then little magic. Algo magia. See. Okay, so when the select line is 0, 0, we're gonna do something. When the select line is 0, 1, we're gonna do something. 1, 0, we're gonna do something. And 1, 1, we're gonna do something. And keep in mind that if we want to simulate this, we're gonna have to say when others, and then like the thing. But we aren't simulating, so I'm not doing that. I don't feel like it. So when 0, the mux out, kind of by definition of a mux, SME. And in general, it's gonna be B. It's gonna be C. It's gonna be D. Right. This is the mux. Done. Right. Hopefully this makes sense. You know, hopefully if I were you, I'd compile now and make sure it compiles. I'm not going to because I have other, there's no reason for me not to compile. Okay. But it's got inputs, it's got outputs, just like every other part. And it's got it's got four functions. Select 0, 1, 2, 3. Hopefully this makes it a little bit clearer when I say like it'll point to this or this. Yeah, here we go. Is expecting end or begin. That's because I didn't do the end on Big Mux. So thank God I compiled. All right, but that's ALU, copy paste Big Mux. I mean, like, what does a mux do, right? It selects a thing based on, so 0, 0 corresponds to A, 0, 1 corresponds to B, right? 0, 0 corresponds to A, 0, 1 corresponds to B, 1, 0 corresponds to C, 1, 1 corresponds to D. Almost. Like that's what this binary number is representing. Okay, when I say 0, 0, it's labeled 0. I mean, like, can it be more intuitive than that, right? So I say intuitive, but I got it wrong. Of Big Mux, of course. And after Big Mux, we have one more component to implement, and then we put it all together in main, and we're done. So stay with me, guys, please, while we wait for this to compile. The boys messaging me. Expecting case. Oh, we need like an end case here. Okay. Cool. Cool, cool, cool. Let me wait for it to compile. And it's compiling, it's running, and okay. So Big Muck's done. Next, Reg. Reg is even easier. You can see that wasn't very much code. I'm going to stick it in this file, so if I need it for reference, I have it. But we won't need it because it's probably very easy. Starting from nothing, the first thing we always need, some imports. That's not what I pressed when I clicked Control C. There we go. I have like an entity, reg, port type idea, like an end reg, right? So what's the register? Well, we look at it. That's insert mode. I want print screen. We look at the register. Sadly, this won't help us much, but I can dream. We look at the register. We have it cover up. That's fine. Leave some, it's covering some wires. Who cares? Looks like register has one input and one output. So turns out registers are made up of D flip-flops. We have Ds, which are in standard logic vector, 3 down to 0. And we've got Qs. Okay. So far, makes sense. These are in, Qs are out. And so it doesn't kind of imply this, but what we're building is really do 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 blah, 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 blah. Got like a clock, got like some D. If you don't recognize this, you should consider dropping because it's a D flip-flop. Oh my God, right? But before when we put like a 0 and then the clock would go high and we get a 0 out here, right? We're gonna make something where we put 0, 0, 1, 0, 4 bits, and the clock goes high and we get 0, 0, 1, 0 on the output, right? It's just a 4-bit D flip-flop with, of course, some like reset. Okay. So what are we gonna do? We need a reset. That's an in standard logic. And we need a clock. It's an in standard logic. Right? And then that's that. But this guy doesn't need a semicolon. Now, architecture, behavioral of register, begin and behavioral. All right, we've got a process. Depends on clock and reset. And we've got like a little begin and end for it. All right. Now, if reset is 1, I'm going to say if reset's 0. I think that'll make my life easier. Then reset. Else if that's not else if, that's ELS if. Else if rising edge on clock, and then we'll have like an end if. All right, we'll update. So if there's a reset, I mean, make the Qs equal to 0. Doesn't get much simpler than that. And it actually can, because if there's a rising edge, then the Qs become the Ds. Hopefully you guys could think of that. Not that challenging, I don't think. We've made D flip-flops before, so just do it with a bit vector this time. I'm going to compile. I'm going to send a selfie to my friend. Cooking. Cooking. Go. All right, syntax error, near text begin, expecting is. It's like begin. Process. Architecture, behavioral of reg. Is begin. Is that really? Yeah, it is. Is begin, of course. Why didn't I think of that? Hopefully you guys appreciate these videos. I've done 3 labs in the past 2 days. Not fun. And a DSA project in the past. If you take the past 3 days, I've been hella productive, but I can feel it in my soul. Okay, we did it, Reg. So we made the ALU by copy pasting. We made the big mux by thinking about what a mux is, and we made the reg by thinking about the thingamajiggy. Notice a pattern. Okay. It's not complicated. There's a very, 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 very easy pattern to follow. We have a process with the things we care about, a case, and then we take actions regarding that case. We have a process with things we care about. We have a case, actions based on that. Okay, we have a process with things we care about. An if-else statement is really just a case, and the case is really just an if-else statement. Okay, it's not rocket science. I'm not pulling something new out every time. What do we care about? What should we do when they change? Um, this case statement, it's all show. It's all show. Okay. So Lab4. So I already have this code kind of like saved elsewhere. So boom, right? You said egg, yogurt, M&M. He's making fun of me. It's okay. It's okay. So we're basically putting everything together. What does that mean? That means we've made a mux, we've made a reg, we've made an ALU. Let's do the wiring as seen here. So we've got an entity. Lab4 is poor. This is the last file we're making. If you're not doing the extra credit, which you will not be getting help from me for, too bad. The ALU, it's got like you saw at the beginning, right? That we wanted it to be on the 7 segment display, so we're gonna have some of that. But thinking just kicking the floor. My poor roommate's probably no idea just kicking the floor. Forgot he was in here. Anyways, sorry, bro. But we're gonna need we're gonna have a we're gonna have the small input bus. This is an in standard logic vector 2.0. You'll see why. You think, but Joe, the input bus is 4 bits. It turns out we're gonna run out of switches, literally. We're not gonna have enough. There will be no way. There is a way, but we're not gonna use it because we don't want to use anything but the D10. Um, upsetting me. But it's okay. It's okay. Input bus is smaller because we ran out of switches. Okay, and I'm honestly drawing a blank as to what to put in here, so I'm just gonna go check. So sure. I mean, kind of feels bad when I just like look at it. I mean, we're gonna have a clock. It's an in standard logic. I'm just gonna keep looking at it because I'm getting tired. Of course, we're gonna have a CN. We're gonna have a reset. What about outputs? We're also going to have the things that control. So these were like sort of basic inputs. We're going to have the select line for A. It's an in standard logic vector 1 down to 0. And we're going to have select lines for B as well. What are these select lines? Like, what do they represent? They're cell A and cell B here and here. Cell B is a Pokemon, by the way. We're also going to have our ALU opcode. I'm going to call opcode. And 2 and 0. Pretty cool. We're going to have the C out. It's an out standard logic. Remember before that we made Cn actually a standard logic vector from 0 down to 0, right? And so just make sure we have that reflected here. My bad. And then we have some 7 segment displays, and I like can't be bothered to type this 4 times after typing it once. So, we wanted to show some 7 segment displays. And that is that. Maybe not super intuitive because we don't know exactly what we're building, at least you guys don't. But this is going to be A, B, out, ALU out, and input bus. Right? So we've got a clock driving the system. We've got C in. We've got reset. We've got select line for A and B. We've got the operation code. We've got the C out. We've got 7 segment 0, 1, 2, and 3. Right? We're going to have an architecture and I spell. There we go. Behavioral of is something like that. We've seen it a million times. Okay. Now we know. We know that we're using the ALU component. We know that we're using the Big Mux component. We know that we're using the reg VHD component. And finally, file open. Stay with me, guys. We know that we're using this decoder. Okay. So we have to declare the components. One, two, three, four components. Here's what it looks like. Component ALU ports and component. So basically we say components, the thing's name, and then end components. Like that. What do we put in the component? Well, you go to ALU for the ALU component, you go to the entity, and you copy everything excluding that last parenthesis and last semicolon. You come in here, you paste. Right, and you tab, and you boom, and you boom. Okay, now we do the same thing for Big Mux. Component, Big Mux, uh, port. Kind of surprised it doesn't say port mat is port, but it doesn't. And we're gonna do an end component. And what do we put in here, Joe? Go to Big Mux. You go to the entity for Big Mux. You copy everything. Notice how I left the parentheses semicolon down here so we can just kind of copy the whole thing because we're omitting this always, right? We put this in here. Oops. Like that. Nice, easy. Next, we're going to have a component called reg, kind of like that. Reg, what do? We copy this, excluding that trailing parenthesis and semicolon. Boom, 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 boom. Nice and easy. Finally, we have our last component, which is the 7seg decode. Is it decode or decoder? It's decode. Whoever named that stupid. It was me. Port and component. Are you guys having fun yet? I'm not. What I get for? Never mind. Boom, 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 boom. So, okay, we've defined our components. Now let's just instantiate them and do some wiring. Okay. Go here, kind of look around, a little look-see. Okay, so it can be very intimidating starting here. In fact, I know exactly how this works. I built this on a breadboard with Dr. Schwartz, and it was intimidating for me to start. So where should we start? Well, top to bottom is a good way to start, and I think starting with the muxes is going to be the best way. You'll find that when you're writing with the muxes, you're going to be like, well, I need signals for the registers. When you're starting with the registers, you'll be like, well, I need signals for the muxes. We're just going to leave some stuff blank. Okay, it's okay. We're going to do a little bit of a two pass. First, we're just going to find the muxes. Okay. So we're going to have a mux A is a big mux. That's going to get a port map. That's what we're doing right now, right? Port map. And then we look at big mux and we see that it has cell, A, B, C, D, mux out. We've got cell, A, B, C, D, and mux out. And the same way we have mux A, we're going to have mux B, but I'll wait on that for now. So the select lines, I'm pretty sure we just have those, right? Yeah, cell A, right there. So we just have that. Cell A. Now, what should A, B, C, and D be? Well, what's the order? It tells us in the lab document that the order should be input, ALU, reg A, reg B. So I haven't created these signals yet, but input, bus, ALU, out, reg A, reg B. I haven't created these signals yet, but I mean, you can guess what's going to go in them, right? And then the mux output, this will be our reg A, these, right? Why do I say that the mux output is reg A, these? I mean, just look at the thing. Where does the mux output go to? It goes into reg A. It's the D's of a D flip-flop. It's the D is the next state. That's why I call it that. But you'll notice that like a bunch of these things are just not defined. Pretty cool. Let's go ahead and define them. Cell A is defined. Signal input bus wasn't defined. We had small input bus, but not input bus. Input bus is going to be standard logic vector. 3 down to 0, something like that. Boom, boom, boom. Okay. The ALU out wasn't defined, so let's ALU out. Standard, it's the same freaking thing. I'm not typing it again. Okay, reg A and reg B weren't defined. Well, I hate to break it to you, those are also, they're gonna look like this. They're 4 bits. Pretty cool. And then reg ADs. Reg A underscore Ds, okay, yeah. D's nuts. Sorry, I had to. Reg A and Ds. Cool. Okay, so let's go ahead and make a second mux. Second mux. Semester's gonna kill me, man. Gonna kill me. Mux A, it's gonna be mux B. Instead of using cell A, we're using cell B. This is the same, this is the same, this is the same, this is the same, but the mux out is gonna be reg BDs, which of course isn't defined. So let's do that. So far, so good. Right? The select signal is gonna be different, and the out signal is gonna be different. But if we look here, the out's different, obviously. The select signals are different, obviously, but the same 0 through 3 go into both of them, and so that's why there were no changes. Now let's make our registers. Reg A inst is a register. It's going to get a little port map. And we're going to look at the reg thing, and we're just going to fill out or think about what goes where. We just got D's, Q's, reset, and clock. Okay. D's, Q's, reset, clock. So the clock's nice and easy because we just have clock defined above. Reset's nice and easy. We just have reset defined above. But D's and Q's. So the Q's are the outputs. That's just reg A. We define that signal up here. That's what we meant. And the D's, well, we have something called reg ADs. So I'd bet, without even thinking about it, that's where we meant for that signal to end up. And now we need to make a reg B. It's going to be very similar to reg A. Reg B. D's, it's going to be reg BDs. The output's going to get mapped to reg B. The reset and the clock are the same. Cool. Register is created. Let's make that ALU. All right. So we've got our ALU inst ALU. It's going to get a little port map. And let's read about the ALU. It's the ALU uses this stuff. ABCN opcode, C out, ALU out. So we've got A, B, CN, opcode, C out, ALU out. Okay, what's A going to be? Consult, we see that A is just the output of reg A. And the same is true for B. CN was just defined above. Our opcodes was defined above. C out is just an output. And ALU out, I believe we actually give a signal to, maybe. ALU out. Yeah. Okay. Next, we want to actually, like, we compile this. We can. We'll see that everything works, but if we put this on the DE10, we wouldn't see anything because we're not using our hex to 7 segment decoders. Now, these decoders are very similar to the decoders you guys have made for yourselves in lab, but like 1110, this is actually E. This is hex for E. So 14. 1111, it's actually F. It's hex for F. 1 see, right? Cool. And I actually did all that without making an error because I'm just that cool. So now we're going to have our 7 seg 0 inst which is our 7-seg decoder. We're gonna do a little port map. It just has input and output. Don't name signals input and output like whoever wrote this file did. Those are typically used. Those are reserved keywords, just like case, in, and out. Don't use input and output, but we use them here anyways. The input, I think I remember saying that I wanted the 0th guy to be reg A. So I want the input to be reg A and the output to be, what did I call it? Just 7-seg 0. 7-seg 0. Okay. It's just that simple. So next guy, I want it to be the 1-inst. It's going to be reg B, 7-seg 1. Okay, next I want the ALU output. So it's copy, paste. Now we're talking about the 7-segment number 2. So we're talking about number 2. We're just talking about ALU out. Case doesn't matter. I'm just lazy. Boom, 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 boom. Boom. Boom, boom, boom. Boom, 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 boom. Oh yeah, and then we have our input bus. Right? That's the 4 things I wanted to put on the 7-segment displays. Perf, but we haven't set up the input bus. So sad. How do we set up the input bus? Well, remember I called it small input bus because we're only getting 3 bits and we want 4. Unfortunately, that 4th bit, we're not going to be able to play with it. So I'm just going to say input bus like 3. That's going to get a 0. Right, and then 2, 1, 0. We're just going to map basically the way it works, right? We want a 4-bit number, but we have a 3-bit number, right? So we have something like this, and we want this. Guess what we're going to do? We're just going to put a 0 here, right? And we're just going to map this down, and this down. Nice and easy. So this is just going to get small input bus. So, right, not bad. Not all. Boom, boom, boom. Boom, 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 boom. Right. Compile that, and that's basically the whole app. I'm going to program it and everything, but couldn't possibly feel worse. So, hope you guys enjoyed. Could feel worse though, because 7-seg decoder is used but not declared. Because it's 7-segment decode, right? Boop, 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 boop. Pretty cool. Been standing all day, which is, I guess, better than sitting all day. But boom, compiled. Great. So now that it's compiled and you've followed along, you're going to go to assignments, you're going to go to Pin Planner, and you're going to cry because I'm sorry. I truly am. But this is how it be. Reset L is A7, so I got to change this to A7. Like that. It's the only change I think I made. So, I mean, I'll go ahead and explain what these mean. So what you're going to do, I hate to break it to you, you're a big kid. You can Google DE10 light pinouts, or you can Google mil.ufl.edu 3701 docs DE10 light pins, or you can message me on Slack and ask me for it. But here are the pins for this hex 0, hex 1, hex 2, hex 3. Okay. You're going to go here. You're going to click on node name twice, and that way it'll sort by node name, maybe in descending order. Yeah. And then from here to here, these 7-segment 0, 0 through 6 correspond to these 6. This one all the way to this one, right? Okay. Now 7-segment 1 all the way to 7-segment 6 correspond to these, right? Okay. 7-segment 2 all the way down to 7-segment 6, they correspond to these, right? You guys are capable of doing this. I believe in you. This one down to this one correspond to these. All right, it's not fun, but you got to do it. I would put the clock on B8 and the reset on A7. Okay. And then we're going to scroll around and look at these slide switches. And we've got our op. The C out I put on D15. That's the decimal point. Pretty cool. The opcodes here. I put opcode 2, 1, and 0 on switches 2, 1, and 0, wherever those are hiding. Yeah, 2, 1, and 0. So you see opcode 2 has D12, and then 1, 0 for opcode 2, 1, and 0. Then I'd put B, cell B1 and 0 on A12 and C12. That's cell B1 on A12, cell B2 on C12. I put cell A1 and cell A0 on A13 and B12. So I've covered these. I've covered these. That's what you put the clock there. I put the small input bus on the last three switches. That's small input bus 2 on F15, small input bus 1 on B14, and small input bus 0 on A14. So F14, B14, A14. So now I've explained these. So it turns out there's no switches left. We've used 10 switches, 2 buttons, nothing we can do. Nowhere we can put the CN, the carry in. But it turns out there is. Look at the DE10. Do you see these headers right here? These are, I think this is 20 by 20. They're 20 by 2. There's 40 pins here. Just pick one of them. We'll leave it floating. We're not going to use CN. Who cares? Right? If you really want to drive the CN, pick one of these. And you can get the name of it from me or someone. I just picked like AB3. I think that's like this one. And if you really care, you can take your dad. I guess you guys don't have a dad. You can take a stick. You can take a battery and put it on there or something. I don't know. I don't care. We're not using the CN. Where else would you put it? Right? We're using all the switches. We're using these buttons. Where else would you put it? Right? So just put it on one of these pins and you can pretend like it isn't used, but make sure you put it somewhere because floating pins are very dangerous on the DE10. They could go anywhere. You can break your circuit. So just put it on AB3. We have no way of accessing this pin. Just think of it as something that's always high or always low. We can never touch it. So with that, I've explained all of them. Beautiful. So did I just close Quartus? Nope. We're going to compile. While we're compiling, I'm going to close Modalson. Yes, I want to quit. A little bit of a hint on how you do the extra credit is you'd go to the test bench, file, open. While this is compiling, you'd go to the test bench because it will take over a minute to compile on my computer. You're going to go to this test bench. You're going to change the component to match the new like Lab4 VHDL. You're going to change the signals to match the components. You're going to do a new port map where you just map the signals to themselves, right? It's called A and it has a signal A. And then you're going to do different tests. But you got to do something with the clock. Super scary. How I would do it is I'd manually just say, like, this, wait 10 nanoseconds, clock goes high. Like, you're going to manually put those edges in, right? And then wait for 10 nanoseconds. So, and then you have like clock low here. And of course, you'd be doing other things as well. This isn't the only change. Clock low, which is clock high, right? So you set up you set up the instruction, and then you give the clock a rising edge. And so you should sit here and watch some output change, but not all of them. And you should see this clock rising edge, and then you go back and you clock 0. So really, the only difference from what we did in the pre-lab is for one, it's a different component, obviously, or not pre-lab, the part 1 is a different component part, obviously, but also, you got to introduce this like set it up with clock low, then make clock high. That's it. Set it up with clock low, then make clock high, right? Hopefully that makes a little bit of sense because some of the thing is clock driven now. Now there's a different way to use the clock where you just set the clock up as like a true clock where it's just going, but I don't think that's very representative of like what we're trying to do in this case. So I'd say just set the clock up manually. Keep in mind that typically you basically just set up a separate loop where the clock runs on its own. But I wouldn't do that. I would do it this way. Okay. We compiled 100% successful. Did we? We did. So I'll flip this open. I'm gonna plug in my DE10. No hardware. If I restart the window, no hardware. I found that hard to believe. Start. 100% successful. Boom. Boom, boom, boom. I'm gonna do some manual testing to confirm it works. Um, that looks good. That looks good. So some things you're gonna do. Take the switches closest to the LEDs, these three, and flip them. See if they affect anything. They should totally affect the leftmost 7-segment display. So here they're the closest to the LED right here, and they should affect the leftmost 7-segment display. Right. Think of them as a binary number. This is binary for three, this is binary for zero. That's the first thing. Make sure that like a reset works by hitting like a little, if the reset works. Cool. So the first thing you want to do is put something on the input bus like that, which is the thing I just showed you. Make sure all the other switches are down, just the input bus, and then click that top button. Top button. Top button's the clock. You should see these two get updated. Now click the bottom button. You should see them go away, right? Um, the bottom button's a reset, right? And the top button's a clock. So if we have load input bus into A and B and we clock edge, the 7 in the input bus goes to A and B. Pretty cool. And right now, the output is the negation of A. So 7 is 0, 1, 1, 1. And so negating that, we get 1, 0, 0, 0, which is 8. What if we and A and B? Well, if A and B are the same, A and B, we get 7s all around, right? 7 on the input bus, 7 in A, 7 in B, 7 and 7 is 7. Okay. What if we OR them? Same thing. What if we add them? Well, 7 and 7 is 14, which should be E. So why is it F? It's F because Cn is floating somewhere true right now. And so 7 plus 7 plus 1 is 15 is F. All right, so let's try and load 7 plus 1 into this, and then this video will be over. Okay, so we're going to start from reset state, 0. I'm going to load 7 into one of the registers, like that. Okay, I'm going to load 7 into this one. Okay, just making sure my code works. This isn't really for you guys. And then I'm going to load I'm gonna load 7 into one. I'm gonna load 7 into both of them. Okay. Then I'm gonna do a sum, and I'm gonna load that into one of them. It got 0 because it's looking at the input bus and not. Hold on. It's a little bit tough to play with because nothing's labeled, but it is cool. Boop boop boop. Okay. Boop 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 boop. Okay. So you're gonna get held, and you're gonna get held, and then I'm gonna. There we go. Hmm. So my C out isn't working, essentially, which is annoying. Hmm. Wonder why it's not working. Honestly, everything else works. Might leave that as an exercise to the viewer, but C out isn't working. So let's look. When 0, 1, 1, the ALU out is going to equal this. If A plus B plus unsigned is greater than 15, C out equal 1. Otherwise, C out equals 0. Maybe I'm not tying the C out to the correct thing. It's possible. Let's look at the ALU. Move my C out to C out. Where C out is a standard logic vector. That's not good. Cout, ALU. ALU says that Cout is a standard logic. Cout to Cout. And then we go to our assignments, our pin planner. We look at Cout. On pin D15. Weird. You should totally. I wonder if I. Hmm. Huh. I'm thinking. Sorry, guys. Don't know why the Cout isn't working. 0, 0, 0, 1, 1. If A plus B plus C. Maybe it's carry. Hmm. 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 Else. Connectable LED. When does this process block get called? When A or B or C in changes. Ah, what else do I have to change? Oh, it should be when A or B or C in or the opcode. Guys, why didn't you tell me? Of course. So what was happening there? Well, A plus B plus CN would change, but the opcode wouldn't. And so this wasn't getting called because it's inside of a process block. So by excluding one of the inputs, I made this not truly combinatorial logic. It became something more, something else. Object clock is used but not declared. It's because it's a remnant of a different thingy. Boop, 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 boop. Right? So if you want your process blocks to be truly combinatorial, include all inputs in their sensitivity list. That's the moral of that story. How long has this video been going? Too long. Too long. All right. Hope you guys like this video. Seems like we're basically at the end, or at least we're very close. I just gotta program this thing, make sure it works so I know I'm not handing out faulty code. Oh, that's not good. That is good. Okay. So let me load like F. Let me load F into one of these registers. I'll load F into this one. That's this one. Really? Hmm. There we go. I loaded F into that. Now I'm going to keep you, and I'm going to keep you, I believe. Nope, it's this way to keep you. Okay, now I'm going to load 7 into A, which means doing this. Okay. Now I'm going to preserve B, and then preserve A. Still not working. I don't know why. Not gonna lie. I got no clue. You'd think changing the opcode would change the. Maybe I'm tying it to the wrong bit. I don't know. Maybe these guys like are unsigned, but they're 4-bit unsigned numbers, and so they just wrap around. So there's a way to do it. I don't know how. It's chill. If you guys are interested in receiving double extra credit and you do this right, I will give you 2 points of extra credit on top of the other extra credit. That's right. Because I'm not doing it. I'm sorry. Too long. It's probably I if I had to bet the thing that's happening is the unsigned number is this many bits. And so if you add like 100 to it, right? This many bits plus like some number like this. Every time when we're performing the addition, it hits to this, it just wraps around to zero, and then one, and then two, and then three, and then four, right? And then it wraps all the way around to this, and then wraps back to zero. There's a way to fix it. I'm not interested. This video is enough. When you're done with this and you're satisfied with it working, you can move stuff around between the registers, perform operations, store the operations back into the registers, etc. You're going to go to Project, Archive Project, Lab4, Part 2. You click Archive and click Yes. And that's Lab4. I hope you guys found this video helpful. It took a lot of work on my part, so if you leave me an excellent Gator eval, it'd make me very happy. Yeah, there's nothing else to talk about. Paint gets closed. I'm just thinking, making sure all this gets closed. Pin assignments are going to get closed. This is closed. Chrome. So yeah, I hope you guys found this helpful. Have a great week.